So just a quick intro, you know, about the group. I'm not going to repeat the slides. You saw that in the past recordings. What we are trying to do is to kind of reduce the gap between IT needs and business needs, because way too often we are like car mechanics liking to pimp the cars instead of driving the business around. And we try to do the change by giving the books to the executives, but because of the changes in IT happening top down. But we change the focus a little bit more to bring more business-focused topics, to offer consulting services, and to be matchmaker between people looking for work and offering work. And we have the forum for you to express your feelings, how we can grow the group further, not just giving those book titles. Our publisher, Manning Publishing, was our sponsor for 3 years now, and we're going to have a raffle at the end of this meetup to give another product of theirs, anything you want to choose. So much appreciated. And then we have a couple of meetups already in the pipeline. Like it's an unusual meetup, Lynn, I'll need your help to promote this meetup. I have a professor from Italy, from Messina. Like it was pure accident that I found out how advanced IoT in Messina is. And now, like 5 years later, since I discovered them, they're penetrating through Italy and Europe. So Antonio is going to talk about projects they do. I'll post the links to his talk. And then in August, Luck from Google is going to talk about, he's head of AI, data analytics in Google. He's going to give us some insights about new work at Google. And also I'm talking to Snowflake to bring them here. And you are welcome, everybody in the group, to talk, no pitching, just sharing ideas, regardless how small or big they are. And also, please rate us on Meetup so more people will discover this group. So this is how I started Meetup before the recording. This is how I stumbled into Lynn accidentally. I thought that lynda.com is her company because there are so many courses you had at the time. That was way before LinkedIn Learning existed and bought the company. And then, like in 2016, I was going through my basement. There is so many talks I still like to print and collect. This big data architecture you did in Sao Paulo. It's the early beginnings of the cloud. You covered all 3 clouds. And why I like you, so beside of good connection, like you're an educator and the way you explain things, it's really easy to adopt. It's not like a show off of somebody who knows. There is your teaching to mind connection, and it works for me. And I'm hoping that world we discover through this recording and other courses what they can learn from you. But the second reason I like you is vendors in the cloud. They're like pizza shops. Everybody brags my pizza is the best, and it's hard to know who to believe. You're the only one I know that is acknowledged hero or like expert or MVP in all 3 clouds, so you can give unbiased opinions. So I listen to you first before choosing services or cloud vendors. So that's how you impacted this group, and I'm honored to have you here. And I hope this is the first in the beginning of the talks on bioinformatics. We just chose Azure because we only had one meetup with Azure topic. So take it away. Thank you so much for being with us.
Great. I'm going to go ahead and share my screen. If I can, let's see. Can I share my screen? Yep. Okay. So I'm really practical. And can you guys see this strange looking narrative genomic analysis of COVID-19? Can you guys see that?
Not yet.
Not yet.
Bottom right, present now.
Okay, let me just try present now, your entire screen. And I will try presenting. And there, you should be able to see it now.
Mm-hmm.
Okay, so, the thing with working in anything in IT is once you have something working, why change it, right? And any analysis that you're doing with data is going to be often mission critical and very expensive and very complicated. And I'm in the serverless group, and serverless is probably the farthest away from traditional data analytics of any other of the IT patterns that I know. So why change? Well, even before 2020, which is being kind of represented here in an interesting way, I did a bunch of work with cancer genomics. And I did it in support of bioinformatic research to help to make that research more reproducible, more scalable, with the intention of supporting the development of personalized medicine. So basically improving human health. Well, enter 2020. Of course, 2020 is a year of COVID. And one of the clients that I had, CZI Bioinformatics, working with the data pipeline, happened to be on AWS. was integrating this downstream visualization tool. So this is, you can think of it like a Tableau, but for genomics. This is a Nextclade. And one of the things that Nextclade does is it helps to geolocate virus variants. And again, there were so many things that were so ironic about last year. Many people know that I had long tail COVID. This visualization was the result of work that the team was doing to improve their pipeline to integrate this third-party visualization tool. And this visualization is actually the variant that I had because I live in Minnesota. And so again, talk about, adding a personal aspect to architectural changes in our work. Because the fact that, the team was working with architects and people like me to help to make the pipeline modern and serverless, helped to get to this information faster. So again, I just think that it's even more important in this time of uncertainty around disease and some of the other challenges that we face, that we have to be even better in our pipelining. So one of the things that I hope that you guys take away is these patterns are applicable not just to bioinformatics or genomics. One of the interesting things about bioinformatics and genomics is in terms of data that has to be analyzed, the volumes are volumes that I've never seen before. Just to give you an example, the Broad Institute, which is again another big player in the space and one of my clients, they are analyzing 45 terabytes per day going into the public cloud. It happens to be Google Cloud. And we're just getting started. We haven't gotten really into single cell analysis. This is still a lot of DNA analysis. So, this is what comes after big data. It's genomic scale data. So the focus of this talk is going to be an article that I wrote. So if you guys want to, pull up the article or whatever, it's an article on Medium. I'm not a huge fan of PowerPoint because I'm sick of it, and especially after a year of Zoom. And so what I want to do in this discussion is to make this more like a university class where we have this article and then I'm going to stop at certain points and then open it up for discussion so that you can understand why this approach was used for this type of problem. So the article is Azure for Genomic-scale workloads. The focus here is Azure, and we'll get into some of the implementation details, but not all of them. But I want to also extend this because I have done similar types of work on AWS and GCP because, as was mentioned, there aren't a lot of people that work in all these different environments. And one of the things that I like to share is things that I've learned. So I also worked with an apprentice, Kelly Camrod, who worked with me in this work. A pattern that I have been doing in my consultancy is I have been bringing along technologists who are interested in getting into bioinformatics because there aren't enough people who understand the cloud side in the current bioinformatics research world. And so I'm trying to solve multiple problems when I build architectures by getting more people in it. So the first sort of thing that is important to what we're going to think about today is this general pattern called a data lake. Now, this is not a new pattern per se, although I find not very many of my customers have actually implemented it effectively. So it's not really like a database or data warehouse where everybody's had one, everyone kind of knows how to use it. Data lakes, I find in reality, are people say they have it or they say they want it, but they don't kind of really understand or they're not able to implement it. So it's kind of early. Generally, when you're working with genomic scale problems, you're going to work not with a database or a data warehouse because of the amount of data. It just simply is not cost effective. I'm going to make a little aside. One of my customers from last year, who I will not name who it is, they had 15 researchers, and because they did not implement a data lake, they implemented a data warehouse. Their Amazon bill was $1 million for 15 customers. And they happened to be well-funded, so they could bear that. But that just was really, really unfortunate to me in terms of the use of their funding. Because had they built on a data lake, probably would have cost, I don't know, 1/10 or 1/100th of that. It is that much cheaper. So as I write here, and as you see in the picture, when you build analysis pipelines for genomic scale workloads, you use the data lake. The data lake uses an underlying blob storage. So in the case of Azure, that would be Azure Blob Store with buckets as the storage. You do not use a database. You do not use a data warehouse. And this effectively separates the storage layer from the compute layer. So you can put various types of analysis in the compute layer. So we'll be looking at one implementation, one pattern on Azure. You also will usually have custom analytics using some of the analytics engines that are available on that particular vendor. They might be SQL, they might be NoSQL, they might be serverless, they might not be serverless. The trend is for these analytics layers to be serverless, but it is something that the cloud vendors are moving towards. So the sort of starting point, if you're new to this, is you have blob storage with various buckets. That's your storage layer. You have a compute layer that has some sort of a job controller. Could be a service, could be servers, could be clusters, could be different things. And then you have VMs, and you could see those VMs as a cluster of VMs. You could see them as a cluster of containers, so Kubernetes. You could see them as an API. And then you have downstream analysis after the compute or the processing has been done. In the case of genomics, you're going to have basically validations, because the genomic data is, comes from people in the case of COVID, for example. So it's spit and blood and everything like that. And so you have a lot of error because you have dirt and noise, and things go wrong in the sensor, in the sequencer machines. And so you have a lot of, they call them QC checks that happen in the processing layer. So this pattern is really, really important in general if you're new to data lakes. How you do this, of course, matters depending on what you're implementing. So files are the data. So you're using the blob containers. And then the job controller spawns the burstable cluster. Really, really key is the security. In general, this is a poorly implemented pattern in cloud. I mean, how many times have you heard about, an S3 bucket on Amazon was improperly secured and personal information was made available in an inappropriate way? So, here we have health data, which has, you could be, it has HIPAA requirements around it. So you could be sued basically if you don't do things correctly. So the vendors are starting to step up and supply additional services which help customers, because it's non-trivial to secure your data properly in the buckets. And it's a baseline of a data lake. So one of the first things that I check when somebody says, I'm going to do a data lake, or I have an idea for a data lake, is what is your security plan? Also, what's your data encryption plan? And if they look at me with a blank face, I know that we have some work to do. Another pattern that's interesting in the middle here, as I write, it's increasingly common to add optimization layer over blob storage. Now, this is an area that I've been doing work actually all year. I just worked on a contract that was comparing a vendor optimization product that sits on top of, in that case, S3, versus some open source stuff, which is what's shown here, the Fuse library, versus vendor products. And this is a real active area in data lakes that the vendors don't really talk about that much, because they just say, oh, use S3, use Azure Blob Store, use Google Cloud Storage. It's great. Well, that's not always good enough. It's often not. It's often not fast enough. So another important part of a data lake is testing at scale to figure out, can you get by with native, let's call it Azure Blob Store access, or do you need something to accelerate? In this particular example, Microsoft advocates using this Fuse library, which is for usability and for speeding up the access. So it's basically designed to run on Linux. Another pattern is the incorporation of cloud-hosted genomic reference data. This is specific to genomics. In genomics, when you're analyzing variants, you're going to analyze against a genomic reference, so 1,000 genomes or some variant of that. And so if that data is already on the vendor cloud, then that's going to make the pipelines run faster than having to upload it. So the sort of larger pattern is, if you're doing data pipelining in a data lake, is the reference data already available in that particular vendor's cloud? If not, can you make it available? How much will it cost to make it available? All right, so more on files. Another thing about genomics is it's not CSV files. It's all these proprietary file types. So one of the considerations when you're building a data lake is you don't have tables. You will eventually create a schema over the top of the files that looks like tables, but you don't have tables, you don't have tabular data, you have file-based data. And the file-based data can need to be optimized. For example, if you have these BAM files, they're binary alignment maps, some of them can be compressed into some of the other formats here without getting too into the weeds. And those compression jobs are run as part of the batch processing. So when you are doing your data pipelining, when you've got a lake, you're going to have different kinds of preparation steps. The preparation steps could be QC steps. They also could be file preparation steps. So kind of like the ETL of a data lake is not, checking the data types in the table. It's maybe partitioning the files, for example, or combining the files if they're tiny into bigger chunks. So it's different types of processing. Again, the key aspect of this is the size of the data is driving change. It just won't fit in some cases in cloud-based like databases or data warehouses, or if you did try to put it in there, you would just run yourself out of money really fast. So, and this is just the tip of the iceberg, because what is really kind of another hot area in genomics is single-cell RNA sequencing. So what that means is sequencing the RNA by cell type in your body. So it's an exponential growth of exponentially growing data. It's really interesting. The guy who ran the Broad joined the Biden administration, Eric Lander, which I'm thrilled about. Clearly, he understands this challenge of this problem, but he always talks about, we just haven't even got anywhere mapping the human genome until we map the entire, every type of cell in the body at the RNA level. That's what we really need, which kind of just all the technologists just groan because it's kind of like in the exabytes. It's like things we've never seen before, which again, you might say, well, I don't have this much data, so like, why do I care? Well, you do. You probably just aren't doing anything with it though. And especially after our year of being online all the time, oh my gosh, we all have so much more data because everything that we've done on our phone and online, which is kind of how we all lived last year, is all available now. And so, this is just sort of the precursor of what's coming. So I think with this, I'm going to actually pause in terms of talking about files versus traditional data and see if anybody has any questions or discussion or anything they want to add about this.
And Lynn, I've got a question about the first one on the Fuse library. You mentioned about the Fuse library. And I don't know, so disclaimer, zero knowledge about, like, really about the scale of the data when we talk about DNA and RNA. But even with that, I'm just trying to understand better the meaning of optimization of files. Like, even in the more traditional data lake, like back in the old style Hadoop MapReduce. So I remember that in the AWS implementation of EMR, like Elastic MapReduce, to talk to a Hadoop file system, they actually came up with EMRFS, right? Is that kind of what you're talking about? Is the Fuse library kind of like that?
Yes. Yeah.
But I guess even more complex.
Yeah, very much so. And the point really is it's the Wild West. And so this is basically like uncharted territory. So when we were doing that analysis of this third-party vendor versus, in that case, it was versus using attached Amazon EBS blocks or EFS, which is Elastic File Storage in Amazon, or raw S3. We did perf tests. Yeah. And like there was nothing. Like I was joking, it's the ungoogleable problem, which is the best kind to work on, right? Because the vendors are just telling you, just use S3, just use blob storage. It's good enough because they're working on it too. But what I'm saying is what I'm finding with my customers is not good enough, especially when you are going, the use case we were talking for that one was called Rapid Clinical. And the idea was like to sell it to hospitals like Mayo Clinic, where they could do like RNA testing for cancer patients, like rapid, like in the hospital as part of your doctor visit, which that's not something that's available yet, but it's been, the possibility of it has been accelerated by COVID.
Yeah.
So yeah.
Kind of related follow-up, right? So again, I go back to my initial, to my experience with Hadoop, right? So there were, there are at least two impedance mismatches, if I phrase it. One is size, block size, and actually structure. So when the compute needs to process things, I remember, I don't know, I think the block size of Hadoop was initially 256 or something like that.
Good job.
some huge number.
Yeah.
Like there's the first mismatches. Like my compute, for it to be fast and efficient, that's too much. Like in, at least the first time I used it, it was in POS retail, and it's just, those are small transactions. 256 is too much. So my first problem is the impedance mismatches. My first thing is, after I grab it, I gotta cut it up into, right?
Yep.
And the other, okay, so the size mismatch, and then cutting it up, laying out the structure so that now it flows more frictionless across the compute pipeline.
Right, and all these things are poorly understood. And so what happens is almost all my clients have problems with their guess what bill. Like typical, I'm picking on AWS here, but typical AWS customers, my EC2 bill. Not Genomics customers. Genomics customers are like, my S3 bill.
And yeah, possible. Okay, so now digging deeper in the genomics world, or in the lots of data world, like what would be an ideal block if I'm still using a block? It's a lot larger than 256, I guess.
Yeah, it totally depends on what kind of computation you're doing on it. Because again, the computation is also more complex. Sometimes you have simple, like find things, select things, or validate that it's a certain string or something like that. But you also have machine learning. Because when you are doing, for example, variant analysis, the way that it works, it's probabilistic computing. They cut the DNA up into little, I call them strings. That's not the correct word, but like, there's 3 billion letters. So you don't analyze 3 billion. You cut it into little chunks. That's how it comes off the sequencer. And then basically they duplicate those, but they don't duplicate them evenly. It's kind of crazy when you first hear it. They duplicate just parts of it, and then they overlay and match it. And then they probabilistically, using machine learning, say, okay, this looks like it should be a G because it's 90% G. But that kind of computation needs a different block size than, is this A, B, or C, like a Boolean kind of computation. So that's one of the complexities of it. And most people, frankly, don't do anything unless it's too slow or doesn't finish. Like, again, we're in the Wild West here because the amount of data just went poosh as the sequencer price came down. When I was at the Broad, I went and talked to the sequencer lead. It was pretty cool. I went into the lab, the room where they had, it used to be, it's a fun fact, it used to be a beer freezer. And it has all these Illumina sequencer machines. And she was saying, up until, I don't know, 4 or 5 years ago, they only did parts of the genome, like the exome, because it was too expensive, right? I mean, this is really, really recent that they're doing the entire genome, because the cost of sequencing has come down much faster than Moore's Law. And then we had COVID, which accelerated it even more. So, they don't know, right? That's why I'm talking about this, because those of us who have had experience from other domains, we can take some of the patterns that we know from those other domains and help here. But there's just so much work to do to optimize. Does that make sense?
Yes. Okay. So I don't want to hog the conversation. One at least for this spiel.
Yeah.
So I ask about storage. Now talking about the compute. Framework for serverless compute. So where I'm coming from is, for me, there are degrees of serverlessness. I mean, one is serverless is I'm unaware of servers. Mm-hmm. Okay, that's one. But mine is my preference is using lambdas, using function as a service, and kind of aspirationally, like if do you foresee
yeah, I know where you're going with this, and the short answer is
yes.
But there is this big gap between what bioinformaticians do and between what the cloud vendors are doing. Mm-hmm. So the cloud vendors are trying to, I'll just put it in a nutshell, create APIs or custom lambdas. They're trying to do that, like, just hit this endpoint and then you're good. Like, I have the genomic schema. You can just put the files in this format, and then Google is kind of the reference use case here. In BigQuery, they have one of the types of files that the genomics people use is called a VCF file, and it basically contains the variants of interest. And so it's a common genomic task to say, okay, I've got the variants of interest. Now let me query this file and find, like, does this variant cause a disease? You know what I mean? Like that. So BigQuery has knowledge of VCF files. Like, Google put that in. So they said, oh, now you can use SQL serverlessly. But the uptake has been poor. Guess why? Researchers don't use SQL. They use R.
Wow.
I know, it's funny, the blind spots, right?
But that's kind of the problem, is that Google should have realized that many researchers, they don't want to deal with it. They don't want to abstract it as a SQL.
Right. Well, there's always opportunities for us as educators. So I'm going to actually jump back into the compute. If that's okay. Hey, no worries. I'm glad. Okay. So let me present and present and present and present. It gives a good break from the article. So compute. I totally agree with what you brought up, that where I would love to see genomics get to is serverless. And I have had one client, CSIRO Bioinformatics in Australia, that they did a bunch of serverless stuff. And guess what? Shockaroo. They got their tools out really fast. They were replicatable in other clouds. They actually took one they built on Amazon. They put it on Alibaba because it was basically your, typical serverless pattern with functions, with DynamoDB, the one we've all seen, right? But it is not that simple because of the types of analysis and because of what the tools the researchers use. So much as I don't like to start with Docker containers, that is where we are at in bioinformatics. Just a few years ago, Docker containers were new for some people, researchers, they still are new, but they are becoming the standard. And this is a very challenging thing because, of course, these researchers learn nothing about distributed compute when they're studying bioinformatics at university. So they don't know anything about Docker. And, as much as Docker is maturing and Kubernetes is maturing, these are still ecosystems that aren't very long for the world. So the pattern that I see, and you guys will be shocked, is an anti-pattern, but this is what I observe in bioinformatics, that most of the Docker containers are basically VMs. And so I see Docker containers that are in the gigabytes, and they have 20 to 100 tools on them, which of course is not what you would expect. You would more expect that you would have one Docker container per tool or a group of tools. So given that reality, when I educate, as I wrote in this article, careful attention to building efficient Docker container images is critical. What does that mean? Well, anything that you can do given that constraint. So any type of optimization, anything in terms of caching, anything in terms of using the underlying set of tools, or if you must include the entire operating system. I know when I first saw that, I just couldn't believe it, how many bioinformatics Docker containers, basically they are VMs. They contain the complete version of Linux. I had one client down Docker Hub because their Docker images were so big and they just crashed it and they got kicked off Docker Hub and they had to go to Quay or K.io. So it's, again, there's a lot of things that, we who have had more experience building more efficient containers can really be helpful. Of course, on top of that, you're going to have a job scheduler and a controller. I have had some success working with Spark because a lot of complex processes for bioinformatics use some Spark library. And a few years ago, Spark was augmented so that you could use Kubernetes as the controller rather than Yarn. And so that pattern has worked, but it's still arduous. It should be easier. So in this case, for Azure, the example uses Azure Kubernetes Service with Docker. You could use Databricks or HD Insight if you had a very small amount of data. But again, the general pattern is to not use Hadoop, kind of go beyond. So don't use HDFS, use the blob-based file system. Microsoft Genomics built a domain-specific set of cloud scaling genomic tools, which includes Microsoft Genomics Service, secondary analysis. So, the cloud vendors are really going all in on this because lots of data means lots of money. And so it's an interesting space from the cloud standpoint because all three of them are fighting it out. And they've got growing teams internally building new types of APIs and services very rapidly. So this shows Microsoft's representation of the genomic workflow and how they are trying to support with tools and services. So again, this is a little genomics-y, but you guys are all here for a little bit of genomics. So you got the ideas of primary analysis, the secondary analysis, and the tertiary analysis. So the primary is, you're working with the raw files from the sequencers. And the secondary is you're doing your quality checks. So filtering, as it says, sorting, merging, sorting, and then you're producing those VCF files or variant calling files that are used for the end analysis. So what's interesting is as genomics evolves, what is happening is some of this lower level analysis is actually moving on to the hardware. So the Broad builds a set of tools called the Genomic Analysis Toolkit. It's a Java jar file. And they are working with Illumina, who is the big sequencer company, to put optimized versions of the GATK onto the Illumina sequencers and to run some of the lower level processes, the primary and secondary analysis, with highly optimized hardware, including FPGA, which is similar conceptually to GPUs. You can offload some of the linear computation that's needed for the variant calling. And so in sort of more normal English, it speeds up and does the pre-processing on the sequencer, so that then the pipelines that we have to build are not as complex. They're more around the tertiary analysis, and we have more of a possibility to build with tools like a BigQuery if we were on Google that could do serverless analysis. But again, I'm getting maybe a little ahead of myself there. So where we are now in terms of computation is the Broad has a orchestration engine for genomics called Cromwell. So this you can think of as an alternative to Kubernetes. And this is kind of an interesting pattern from genomics. I know Financial has some like this as well. This is like a purpose-built compute orchestrator. And by purpose-built, it includes a language. So Cromwell itself is built in Java, and it's a jar file, and it's an orchestrator. But how you work with it is this higher level language, which is WDL, or workflow definition language. So you can think of this as a domain-specific language for bioinformatics. Kind of like, in a way, like how Terraform is a domain-specific language for cloud infrastructure across the 3 different clouds. So WDL was originally used inside the Broad, but it is completely open source. And it is now, it's been being used by many different research organizations around the world. And you use the WDL language to orchestrate your compute layer. And it integrates with the GATK toolkit. So again, trying to maybe make this more English-like, these domain-specific controller, language, and tools were written and open-sourced through the Broad and have high adoption in the industry. And so this is how Microsoft built this pattern. So what they did is they created a series of tools that integrate with the Broad's tools so that you could then build a genomic data lake with these tools on Azure. And this is all open sourced on this repo, on the Cromwell on Azure repo. And again, we tried to make this as clear as possible through our diagram. So the Microsoft implementation of this is you use blob storage. And the compute layer, you use this library called TES Azure. And then a key service here is a service called Azure Batch. So this 3-part, Cromwell, TES Azure, and Azure Batch. This is a replacement for like a Kubernetes, or if you were doing a cluster of VMs, like a load balancer. And you might say, well, why do you need these 3 things? Which is a good question. And took me a long time to figure it out, because when I first saw this architecture, one of the reasons I wrote this is I couldn't figure it out. I was like, why do you need these 3 things? Why don't you just use a load balancer? Why don't you just use Kubernetes? I do not understand what these things are for. So my take at this point is the importance is the domain-specific integration into the bioinformatics tools, because these patterns for analysis are known. So rather than writing a script or something every time, like taking BAM files and merging them, sorting them, you use a tool from GATK to do that. Doing variant calling and read quantification, which is quality checks, you use tools from the GATK to do that. And to use those GATK tools, which are basically Java tools, you use Cromwell, and then Microsoft has written this integration, this TES, and you integrate with Azure Batch. So the sample to set it up takes at least a half an hour. So I'm obviously not doing that live, but what I did do is I wrote out all the instructions in simplified form. They are here if you wanted to do that. It's not, I mean, it does work, but I like things as simple as possible. So the concepts are: you set up a resource group. Love Azure resource groups. They're fantastic. And then you have to set up your quota allocation for low priority CPU cores. So a pattern around burstable batches that is being taken up by bioinformatics, that again is reusable, is this idea of don't just use regular VMs. Use some sort of like on sale VMs. So in Azure, it's low priority CPUs. In Google, it's preemptible. And in Amazon, it's spot instances. And I mean, you can really save a lot of money, like 90% of the cost of compute. And so this is a really important pattern that I don't see enough customers in general using, because they just don't, they'll get the really high cloud bill for their VM usage, and then they'll figure it out. So you want to do this. And then you have to set up a pay-as-you-go subscription in Azure. Unfortunately, the free tier doesn't allow you to do this. So it's a little bit of stuff you have to do. Then you want to use the default service prefix, Cromwell on Azure. And then you have to have README permissions. So if you're not super familiar with Azure, this is what it looks like after you run the batch setup script. So you have the resource group, and then you have the various resources that are set up. And then I have a link to my screencast, which once it's set up, then you can actually try it out. So again, this is linked, and that's it's like 7 more minutes. So I'll let you guys watch that, but I wanted to kind of go through that while we're talking about it here. So again, we're using files as our data, and we're using a series of containers. One of the things that's like a little bit just confusing, I think, for people when you're using this pattern is folders are logical, not physical. And this is manifest in the way this works. So you'll see folders pop up as the batch is triggered, the in progress folder in particular. And then as the batch completes, the in progress folder will just delete itself. Which kind of freaks people out because they're like, what? But again, this is a blob store. It's not a, files on disk per se. So it's just a sort of a logical container. So the way this thing works is you just drop a trigger file, trigger.json, into the new folder, and then that will generate a job to kick off. And that will move into the in progress. And this is all in the blob containers. And you have to keep on refreshing, which crazy. Of course, you guys should know this, being the serverless group. In the world of serverless, you don't go to the servers, you look at the logs, right? So that's, obviously a huge pattern that continues through in this kind of implementation. And then the job results are found in the Cromwell executions container with the job run and the GUID. And the examples conveniently use tiny data sets. So again, we should know this from anything that we've done with working with data. A mistake that I see a lot of people make when they try to build these data lakes is they do not test at scale. And then they rush it into production, and some, mistakes that they've made become very costly. So I will advocate in these kind of environments that you want to have what I call the tiny data set. That's like the hello world. Then you want to have the small data set. That's the 1 minute. Then you want to have the 15-minute data set. Then you want to have maybe the 1 hour, and if possible, a production. One of the challenges in bioinformatics is it's kind of all or none. Like this storage client I was working with, they were telling me, oh, our Amazon bill's getting big and we're testing this. And I said, why? And they said, well, every time we run it, it takes 16 hours. I'm like, what are you doing? Like, where's your hello world? Like, come on. There was another project that I worked with where the hello world took 8 hours. And I really pushed back on that. Again, to me, these are the kinds of things that we as experienced technologists can really bring to the bioinformatics community because, no fault of their own, how would they know this if they haven't seen it before? But again, working with a lot of clients and just helping them to make a small anonymized data set so they could get rapid feedback rather than waiting 8 hours, helps the project in general quite a lot. So, but this is a problem, right? The other thing is, how do you anonymize data sets? I know there was another client I worked with, they're working with human health data. So that's just like another thing they have to do. And there isn't really a lot of good tools or some open source stuff. But I've seen projects like spend a couple weeks getting these data sets, which again, I'm sure this will be improved as the ecosystem advances. But this reminds me in my career as a technologist of some other ecosystems when they were really new and kind of like you had to do all these things manually. All right, I think I am going to pause because I could just talk forever here and see if there's any questions.
Hey, Lynn, I've got a question.
Sure.
Yeah, amazing information as always. So you alluded to this a couple of times, like, the Wild West and such, and the cloud providers really going, ooh, money, look. So I'm wondering if there are benchmarks that folks can utilize with standardized data sets they can tune their pipelines with. No, there isn't.
No, there's no TPC. No, it's crazy.
Yeah,
like, I asked that too, and I'm actually trying to work with some people and make them, because I'm like, some people, they've literally said, well, if it completes, and I'm like, what? Are you kidding me?
You're going to wait that long? You're going to pay that much? Yeah, that's crazy. Well, obviously, it's in the cloud provider's interest not to have benchmarks data sets, but hopefully folks like yourselves will whip something up.
Cool. What else? What else?
So, Lynn, hi. So I was just wondering, like, when you get when a company approaches you and say, we have this amount of money, how do you parse, like, from a high level, like architecture perspective? How do you know how much can you do with that money? How much can you process? How much capacity can you buy? Where the problems are going to lie? What is your backup and things like that? How do you plan?
Yeah. Well, it's again, it's really I apply a math approach to it. I mean, I'll make another example from another client. They were like, okay, we have this pipeline. This is a typical one. Like, it ran in R. All the tasks are in R, which is single threaded, of course, on my desktop. And I made a pipeline, and now we're ready to go, full on with our data set, and we want it to be on the cloud. And I said, whoa, wait a minute here. Let's get some sample data sets. And they were working with human data, and in this case was our single cell RNA. And they said, okay, I guess we can get mouse data or whatever. I mean, even questions like, where do you get these data sets, right? Like, I don't know this. And so it took them, 3 weeks, I think. And then they had to downsample the mouse RNA data sets because they were too big and da-da-da-da. To me, it's this opportunity, because these practices that we know from having worked in enterprise data warehousing, in working with relational data, these practices are just not known because the volumes of data weren't significant just recently. And so, we went from just small amounts of data to just whoa in 4 years. And so, of course, there's this just craziness around what can you do. And so the other thing is the pipelines are, because they write them on their desktop, right? They're super complex. And so that's been another thing I've tried to help people with. Like, okay, you have 27 steps in your pipeline, and you want to have, 17 terabytes of data the first time you run it on the cloud. We need to break that down. We need to break that down into what are the sections of the pipeline. And again, this is kind of common sense stuff, but the problems these people are trying to solve, like what are the most effective COVID vaccines? They're really serious problems. And so they're not really caring. They're just like, I want to get this up there as fast as possible. So by just using what I consider like common sense practices, like, okay, let's get these small data sets and let's just break down and have the 3 tasks from the pipeline and get that part running. And you know, things that we know work, that helps with cost predictability. Because again, I have had customers that are just like doing the wrong things, basically, and having just, well, I have all these stories. Another customer, well, it was Google. I won't say who the customer was, but you guys will laugh because it's serverless. It's a great service. Google came over and they showed the researchers how to use BigQuery. And the next day, one researcher said, this is awesome, and did one query, and the bill was $83,000.
Yeah, but the problem is, I mean, I'm assuming the customers that are coming, they're coming with a fixed budget, right? And they would say, I don't know, I have a 10, 20, $100 million, yep. and here's the amount of input data. So you start from the sequencer data, right?
Right.
And then you would say like, okay, what do you want to, like, this is we can get a lot of information, but where is our interest point in this data? What is it that we're looking for? And
yep.
now you start going through your process, right? And now you have to calculate like, what is your transient data, which is what is the data that you have to keep for longer term, I assume, right? So at what point would you say during this process is that you become fairly certain what is the cost going to be? And when you approach them, what is your initial estimate versus what is your buffer when you're predicting these things?
Again, it's just so different than what we're used to. They only care about getting the answer. And one of the ways to really help is to try to think about offloading some of this processing, like I was talking about the Illumina example, so that these QC checks can get it down to the VCF file size. Because what is done now, and it depends on which domain, but I mean, COVID is sort of the classic example here. They want all the data. Like, that's non-negotiable because you're in uncharted territory and you're looking for needles in haystacks that are, you know, the whole thing is like unknown. And so they have to have all the data. So you have to figure out how long till they blow their budget. And then it's a different world. And then you go, you know, like they have to figure out how to get more grant money or whatever it is. So there's just so much volatility because, again, like with the Broad's COVID pipeline, they started out and they did that one completely serverlessly, which is fantastic. And, you know, they were doing, I don't know, I cannot remember the numbers, but I mean, it's like this. And when last September, when the schools went back, I mean, they were just heroes because they said, okay, we're going to 100x or 1000x our pipeline and test all the school teachers and test all the whatever. And they really saved a lot of lives. And they weren't concerned about cost because it was public health. So I don't know. It's very like, it's kind of because I did a lot of like enterprise data warehousing where it's like cost. So we have to have fixed cost. It's not that way with this. It's more a question of how can we optimize, and we'll worry about the cost later. And I think that's because of the nature of the problem here. So I don't know if I'm exactly answering, but.
No, it's close. I guess you're saying there's a hype around it, so there's a lot of money floating around, but I'm assuming the hype will go away and it will become relatively normal field in the future. So with asking more predictability about the pricing and, you know, what you can do, because many other companies will want in, I assume. And but not everybody has unlimited budgets, right?
Well, again, I mean, some of the things too is like, as things that I've done is like go for the obvious. Okay, like I said, the cost is often the storage layer. So storage has different costs, right? Like, you know, you have 5 different tiers of storage in Amazon, for example, like, you know, the 5 nines, and you have infrequent access, then you have reduced redundancy and and, you know, so asking questions like, okay, of your cloud bill, what percentage is storage? And then looking at that and saying, okay, do you really need, you know, the highest level of hot storage for all this data? Do you have any sense of when this data has been accessed? mean, I've done that for customers and saved them tens of thousands of dollars because they are not sophisticated around these cost management practices, most of them. And so where we are now is optimization. I mean, yeah, we will get to more maturity, but because it is just like this bombardment of data trying to solve these problems, it's like, okay, where can we optimize? So, okay, I'm going to go back unless anybody has another question. Nope, okay. All right, so now, all right, so again, some technical detail about this Azure implementation. This uses, I was kind of surprised it used Docker Compose. So one of the things that I see out there sometimes is use of technologies that I wouldn't consider state-of-the-art. I'm not a huge fan of Docker Compose, but okay, that's what this uses for Docker containers. So it implements the Cromwell service in server mode. Remember, that's the job controller here, like the Kubernetes, but for bioinformatics. It starts Cromwell as a web server and exposes the REST endpoint. And then the VM serves as the WDL job coordinator. And then because it's Microsoft, the service is written in C# in its trigger service. The trigger service is just a simple service, fires when a file is uploaded to a defined blob container folder location. And the job controller hosts the 4 Docker containers. Cromwell, MySQL. MySQL is used as just the job information. So you do want transactional data for that. Tez, and then the trigger service. And then Azure storage is mounted to Cromwell server using blob views, which is another library around optimization of blobs, which again, hopefully you guys are getting that pattern. That interesting when you see actual implementations of data lakes done by the vendors, you see a lot of these little shims and libraries to make the blob stores faster. And so the Cromwell server uses the task execution service backend for Cromwell. Cromwell, again, this is a little bit technical about Cromwell. You'll remember is the Broad's orchestration server that works with WDL. Cromwell works with different backends. So it can work with Tez. It can work with Google, the Google batch, which I forget what it's called, or AWS batch. And the reason you use these batch services on the cloud vendor is you can then configure them to use the cheap VMs easily. So like I was saying here, it's the low priority, which saves a lot of money. And yeah, here's about the Azure batch. So is that clear? I mean, that's a pretty important point. That it took me a while to figure that out too. Why aren't they just using a load balancer? And the reason is you could technically use a policy with a load balancer, but these batch services are designed for spiky batch workloads that you can utilize these low priority VMs for cheap. So that's a real important, real money saving process in these data lakes. And Tez was there for authentication, security, integration. So basically Tez is like integrates with Azure services. So this in the other cloud vendors is more full-fledged. In Google, it's called Google Life Sciences, which then works with, God, I can't remember, GCP batch, I want to call it, but that's not right. And then in Amazon, it's Amazon batch, and then Amazon Genomics, I think. Anyway, it's the same pattern. It's like a little integration piece, and then low priority. And then this just talks about it working together. This is what the trigger file looks like. Basically, you say, okay, here's a WDL file that does some steps, and here is a test JSON file. And in the Azure implementation, the logs are viewable in Cosmos DB, which is the Azure NoSQL database. So like in AWS, that would be in CloudWatch logs. In Google, it would be in monitoring. But in this case, it's in Cosmos DB, which I'm not really sure why I wouldn't just go to regular logging. Maybe because you can query it, maybe. And then you also have monitoring, which of course is super important in any sort of burstable situation. So we have Azure Batch that can be monitored with Application Insights or Cosmos DB. So this is where you are doing your sizing. So how much CPU you're using. So this goes to the question that was asked about predictability of cost. So when you're monitoring to see whether it will complete, how long it will take, and then getting this idea of cost. And then moving to verifying scalability. So in this example, we've got this tiny data set. So in the real world, the next thing that you need to do once you get it working is you need to look at basically the cluster of parameters, which is the challenge, again, when you can't be serverless on the compute side. Figuring out the configurations is really, really arduous. So like, which size, what kind of VMs do you need? What are the CPUs? What's the configuration? What's the caching mechanism? One of the things that is cool is you do have a log visualizer called Azure Application Insights. So you can see by task where the overhead is coming. This is called X-ray in AWS, and Google is actually working on this too. I find this to be really helpful. I'm kind of a visual person, so rather than poring over the logs, I like to see this visualization of the entire workflow. It really helps me with optimization, and customers seem to really like it too. So then I go and talk about the two different ways that you can do this, and the general approach is either kind of non-domain specific, so Kubernetes with containers, or domain specific, which is this approach. Kind of interestingly, I worked with the team in Australia on the more generic approach, the Kubernetes with containers, and we got a really, really, really good result at scale. We had a data set that had taken on-prem on an on-prem shared Hadoop Spark cluster, 500 hours for one run. And with using Kubernetes with containers as a data lake, we got it down to like 10 minutes. So that was a pretty big win. That was actually how I got introduced to the Broad, because they were interested in that. So the question is, like, this is kind of the key question. Like, this is more at the vendor level in terms of cloud vendors, and this is more at the bioinformatics level. So, an area to continue to work on is which one is going to be faster at scale. I mean, my guess would be this one, because the vendor, that's their job, right? Whereas these guys are more focused on the domain specific. But I mean, to be fair, these workloads with Cromwell are really the workhorses out there. I mean, the Broad is doing some of the most important human health research on the planet. So if you've got something that's working, it's not always the best approach to say, well, there's this other thing that might work better. And in fact, I think they are doing some work to integrate with Kubernetes. I haven't done any projects with them recently, so the last time that I heard. But this does really, really vary from kind of the general information about data lakes. Like if you go and you look at data lake information, this is from Databricks. This is what the vendors will show you. And my sort of thing that I'm wanting to convey today is this is a great starting point, but this is not really related to what I actually am seeing in genomics. This is just too generic, basically. Like, genomics doesn't generally have a need for events because it doesn't have streams coming in. So we don't have an event hub piece. Genomics generally doesn't have a need for a Spark cluster anymore. You can run sort of dynamic up and down. But I mean, other domains do. So, that's kind of one of the big takeaways is data lakes to be effective are going to be some implementation of the standard pattern. And one of the things that's kind of interesting is sort of new on the world of data lakes is this idea of what's called a data lake house. And the idea, and it's shown in this diagram here, is to integrate a data lake with a data warehouse. So Databricks has come out with something called Delta, which is the ability to integrate and do federated query, where you can query sometimes the data in your blob store and sometimes the data in your data warehouse, and you can federate. And in fact, I am actually currently in progress writing a book called AWS Lakehouse Architecture. So I am actually working on this with Amazon. So it's kind of interesting, and there's customers, most of whom are probably going to not be genomics, that pattern would be important as well. So now I'm definitely going to pause because I've been talking and I'm thinking you should have some questions.
That is amazing. Thank you so much. Who's going to start first?
So yeah, I'll jump in there again, Lynn. Thank you. Totally fascinating. You know, we talked earlier on the call about the security of that data, right? And, you know, typically how that's not even part of the conversation. But, you know, inevitably, there are regulatory bodies that govern the jurisdiction of where that data resides. And I'm just wondering, like, how common is that conversation, or not common, when you're talking to these folks that clearly have the best of intentions and, you know, want these results, but, and just like any development team, don't want to be hindered by quote unquote security?
Well, laws help. So HIPAA helps. You know, if I could compare this to like my long time ago ad tech days where they had no security, like none, like they didn't want to do it ever till they, I don't know, like got hacked or something. You know, at least in health, there are laws. And so people know they have to do it. Now, how they do it, still, I would argue, could be improved. For example, most of the cloud vendors have key stores now. And it's just one of those questions I ask, like, are you using the Azure Key Vault? And if the answer is, yeah, great. Or if the answer is, what is that? Well, then we have some opportunity. Because, again, you know, I don't fault these guys, these people, because they have so much to learn. Can you imagine the amount that they have to learn given the advances in the science and then how fast the cloud is moving? Like, I just consider it sort of exceptional if they do know good security practices. But I see a lot of roll your own. I see a lot of bad practices around key stores. I see key values. I see, you know, everything in one big bucket. You know, just all the bad things. So, you know, my solution to life's problems, as was mentioned in the introduction, is to make a course on that. And so I have, you know, security courses on Linda, AWS security, Google security. Please use security. I mean, it is kind of, you know, the common problem. Werner Vogels, who's the CTO of Amazon, like before COVID at the conferences, he didn't even talk about any of the AWS services. He just basically talked about best practices for security, kind of like customers. Please use our security. You know, it's interesting because I actually like security. In a different world, I could have been like a security professional. And so I just kind of do a cursory look all the time and try to help customers. But it just seems like for some reason, a lot of teams just really aren't that interested in it. It's just not an interesting topic, which I just can't understand. I mean, like literally, my credit card just got hacked again, does every year. And the fact that it does, and the bank immediately stops it because they have good security, why can't we have that everywhere? Like, why is that hard? Or why is that, I don't really quite understand why that isn't considered just part of what we do.
Well, I think you touched upon it actually, because we're talking about such domain-specific expertise where these people are coming from in the genomics place, and they're not security engineers, and they're not even necessarily software developers, and they're certainly not cloud architects, even though they're obviously becoming some. So, you know, there's this abstraction away from the mission versus the tools, and not to say it hasn't always been that way, but, you know, that's why there's so much value in folks like ourselves, where we can be that missing glue in betwixt, right? Provided that there isn't kind of an exclusivity mindset where it's like, oh, you're not in research, you're not in medical, we can't really work with you, kind of thing. So I think that we need to break down some of those silos where it's like, hey, you guys have this mission, love it, let us help you with that, let us optimize it, let us help you secure it, as opposed to them trying to grow that expertise in-house. Not to say that they can't, but it just might be a longer road for them.
Yeah, and the third pillar is the cloud vendors are starting to fill it in. Like AWS has lake formation, which is a set of lake permissions. So it's a superset over the top of IAM permissions. And I think Azure has something like that too, because it's really hard. I mean, if you think about writing specific, if you've done it before, like templated IAM policies and testing them, I mean, it's an expertise, right? And then when you're in a lake, you're connecting different services. So how do you make sure that those work across services with the proxy accounts and all that? So the vendors are starting to solve for that, which is really good. So our job is increasingly becoming like know how to use those higher level tools ourselves, because it's going to make it better. And then even higher level, what's starting to happen is vendors are starting to build purpose-built lakes. So an area where this is kind of hot across all three vendors is around medical records. It's FHIR. I forget what that stands for, but it's called Fire Server. And the idea is to incorporate basically the lake architecture, but to use, for example, known schemas for medical records, and to use things like natural language understanding that are preloaded with medical schemas, so that records can be read and augmented, and to make this process configurable more than creating it. Like you take these services, these purpose-built lakes, and you implement them. But I don't see that yet for genomics.
But with the dollar values you're talking about, I mean, it's such a tangible use case, like even though this is highly specialized and highly optimized, because the only place you can do things at this scale is the cloud, there is a very significant justification for the cloud vendors to build this out. They're literally the only place that you could build this out, provided that you also had the expertise as to know how to optimize the workflows. But to your earlier point about budget wasn't even a concern for some of these projects, it's quite interesting because the cloud vendors are like, come on down. You're the next contestant. So it's really interesting. And they may not even see themselves as having to optimize their pipelines. They're like, well, look, we just need answers, just get out of the way. Optimization just takes time and it's just going to slow us down. And of course, we know that's not necessarily the case, but that may very well be the perception. So there needs to be kind of like sane voices interjecting. But before you can have sane voices interjecting, you need them asking to have the conversation, or asking to have us be part of that conversation.
Right. Well, again, one of the things that one of the reasons I like to give these talks is I leave a trail of my own learning. And I have a repository on GitHub called Team Terry. Terry is the reason that I got into this. Terry is a friend of mine who is fine now, but 6 years ago she got breast cancer, and she was unable to get personalized treatment because at that time the immunotherapy trials were not available in her case. And so she had what I would call dehumanizing chemotherapy. And that is why I got into this, because at that time, my daughter was at Stanford taking cancer bioinformatics. And she came home, this is 5 years ago, and said, Mom, these guys aren't using the cloud very much. And I said, what? And at that time, Google actually reached out to me and said, there's this bioinformatics research tool called Galaxy Project, and they want to learn how to Dockerize and be on the Google Cloud. And although I knew not a darn thing about bioinformatics, I knew that I knew something about Docker. And then when I saw some of the founders talking about reproducibility problems in published research, because the infrastructure for testing was not was scripts basically, and what Docker containers could bring to that, I said, okay, I'm going to start working in this area. And I really I started with no knowledge, nothing, and I documented my journey on my repo, Team Terry. And it just starts with this is what DNA and RNA is. This is what a sequencer is. Watch these videos on Illumina to see how the processing is. And I mean, I am the reference use case if you want to do this, because I just basically made up my mind. And, I work with the Broad. I work with CZI Science. I work with Imperial College of London. I work with all the people in the world. And, you know, I'm not a rocket scientist. I do not have a degree in bioinformatics. I do not have a degree in, you know, even computer science. I have a degree in linguistics, which is probably useful because all the different words are just like foreign languages, like taxonomy to me. But you know, it's really gratifying when taking some of the work that I've been involved in other domains that I consider to be a lot less socially significant, like ad tech, where we serve things up in milliseconds, and turn some of that knowledge into pipelines that go from 500 hours to 10 minutes. I mean, my dream is interactive query. When I went and talked to the people at the Broad, and I got to talk to everybody, I got really lucked out when I first went over there, all the way up to the, you know, people that run it. And literally one of the guys said, "Who are you and why are you here?" It was pretty hilarious. And I said, you know, kind of my story, and I said, okay, what are your problems? What are your challenges? And they all said N by N by N. Which is, you know, I talked before we recorded about one of the other areas I'm learning now, which is quantum computing. And that's why I'm learning it. Because that's, you know, if you have any dabbling in that, you refactor the algorithms to a quantum portion, because then you have the quantum speed up. And that's the dream.
If you guys have questions about that other topic, you can repeat what you shared before we started recording, the book and the club.
Okay, anyway, so I got a little bit off topic. So the big things that I want to share is this data lake pattern is an important pattern in cloud, and the serverless aspect of it is at the data layer, for sure. And it's much more complex than it would seem to put files in buckets, securing it, optimizing it, partitioning it, setting it up for the right workload. The compute part is much more muddy. There is some points of light around serverless. I would point out, like I was saying, BigQuery, understanding VCF files, but you have to understand your customer. And like I was saying, researchers don't use SQL, right? So, or aren't using SQL. I actually wrote a little course on that, of course, which I put on open source. But
can I ask a question? Why don't they use SQL? Is it because the data is really not relational, or it's really because...
Yeah, they don't learn it. They don't learn it in school. So what researchers learn in school is they learn R and Python, or MATLAB, or, you know, SAS, or statistical languages. Depends on which school they go to. Some of them are starting to learn TensorFlow, and Google has augmented TensorFlow. It's called Deep Variant, to help to, again, find the variants faster. But you know, you keep getting these mismatches. Like I was talking to some researchers about, like, why aren't more researchers using deep variant? And they said, well, because deep variant finds individual variants, and in human health, it's multiple variants, which I'm not even a bioinformatician, and I can figure that out. Like, if you have 3 billion letters, one difference is probably not going to be significant. It's a combination of differences. And so they said, you know, great tool for finding a single variant, but that's not the problem we need to solve. So this is kind of an important thing, right? Like, we work in service, if we're in this industry, of the researchers. And I think that that's maybe new for some technologists who are at the top of their game. You know, you have to really think, like, we don't understand the problems. That's why, like, when I went to the Broad, I was like, okay, what are your problems? What do you want? I'm not saying I can solve it, but I'm saying I want to understand what you want. Another example, I mean, very tactical, would be like the typical technologist would go in and say, use Kubernetes. Why aren't you using Kubernetes? Why are you using Cromwell? And I mean, I did have that instinct, right? But I was like, roll that back and say, why is the Broad using Cromwell? How does it serve their needs? And how can I make Cromwell better? Rather than, oh, I think Kubernetes is better because it was made, you know, by more technologists. It's a mindset. And I think, honestly, if you want to work in this industry, computational bioinformatics, and you don't have bioinformatics, if you have that mindset, at least for me, like, I have more work than I can do, right? And I'm constantly learning, right? But I am not an expert in this, but yet I have more customers. I have to turn customers away. So I think it's that approach. So go ahead, you had a question.
The other, so the fact that the end client is not using SQL would be the explanation why you had to come up with that we needed to use a Cromwell as an orchestration of the compute. Because part of me, where I'm coming from, my question is, so by nature, in previous life, I was a DBA. Kind of the way I look at it about the way I've approached Hadoop and data lakes and block storage is, hey, we just deconstructed what used to be a monolithic SQL engine, and all of these ways of like a dependency, a cyclic graph is just, it all used to be just in the Oracle engine. Now you cut it up apart, and that's why you need to orchestrate the compute. So, but because what I'm just trying to understand, because the client is interacting with the data, not in a relational way, because it is not relational. That is the reason why you got to come up with a domain-specific compute orchestration layer.
Well, no, there's actually a couple of reasons. First, you're separating the data from the compute, okay? So that's very different than like your traditional databases. They're separate. And then they're both distributed. So the data is distributed, because you know how a blob store works, like it's in 5 different places, right? And then the compute is distributed, right? So that's the kind of the architecture. That's so it can scale, right? The reason for Cromwell is because you have these tools that are scalable. So that is appropriate to this, that are genomics specific. So like you say, Mark, yeah, right. So they can run on that distributed layer, right?
Okay.
That's why. So like the big thing with the Broad and really beyond the Broad with the GATK tool set is they wrote this distributed set of tools, which didn't exist. Like, you know, because again, a lot of people are still at like the Python and R scripts, right? Which don't scale.
Yeah.
They don't scale, right? They can't, it's almost impossible. Like R is just,
Okay.
So, hey, what else? What else? I was really talking a lot there.
No, for me that was good. Thank you.
I got a sort of an observation. Is just what I've seen in other areas of data analysis. The way things have evolved is maybe it's like financial analysis or log analysis, and just much simpler than what you're talking about here. But the way they've evolved is you start with what you've got as your pipeline, where you're dealing with flat files, and you've got a primary analysis, a secondary analysis, and a tertiary analysis. And then over time, as the technology has gotten so much better for dealing with data streaming of the way that both the technology of the data in the stream and the processing of it and so on and so forth, the primary analysis and secondary analysis kind of moved into the stream, and you still have the data lake, and you still do your final analysis out of the data lake, but it's pushing the primary and secondary into the stream. And I was just thinking, it just made me think of that, because you had said earlier that, you know, you didn't see a place maybe for streaming in something like this. When you were showing the picture at the bottom of your slide, it was, or no, it was the other deck or something. But I was just thinking that, I guess, as the technology increases, like now streams are processing gigabytes and gigabytes a second, not terabytes, but gigabytes and gigabytes a second. Like maybe there'll be a time where that same kind of pushing down can happen. Just like you mentioned that they're putting some of the primary stitching together right out into the sequencing machines. You were saying that they're actually installing firmware now on the sequencers, which do that step. It may be possible that you have a system where, as the sequencer is processing its information, as it gets more and more information, it's streaming it over to your analysis place, which is stitching it together, putting it in the data lake, and then you're ready for your tertiary analysis. But maybe it's just too much of a pipe dream right now, but interesting.
Well, that's how we make things possible. I mean, even doing, you know, the rapid clinical, which is, you know, streaming, I think is like next eventually, but
down the road,
but the rapid clinical, where you're like in the doctor's office and you get the results of your RNA analysis, that's kind of where it seems to be right now, as I'm moving from the from the research into the commercial, which to me was like super exciting, because like what had happened previously, if you were on, let's say, a cancer trial or something like that, you would get your tumor sequence, when you would send it out, you would wait 2 or 3 weeks for it to come back. And, you know, those 2 or 3 weeks could mean the difference between life or death for some people. And so this is potentially really game changing to get the results back in hours.
And what's that architecture where you say that something can run in the doctor's office? Is that where the machine does the initial analysis, and does it send it to the cloud? So it's doing a cloud okay.
Yep,
it's not all on-prem. No.
Yeah, totally. It's totally, and it's specialty hardware. So FPGA, again, Amazon uses FPGA, has FPGA available, which with GATK, there's a version of GATK called Dragon. I don't know why they have to, you know, it's always different names, right? But it runs, I don't know, like 100 or more times faster. And so they use that. And then on the back end, like this project I was working on, this cloud storage vendor, which had been used before by like fintech and stuff like that, they had us write use cases for their sales team, basically to go to hospitals and go, look, this is possible now. You buy us, you buy this cloud reference use case, and you can do rapid clinical, which, I mean, like, it's such cool work, man. Like, come on down. You know, I mean, this so much beats like, okay, we delivered the ads in, you know, 5 milliseconds rather than 15. Like, I used to do that. I'm not proud of it, but I did. And this is so much better.
But that's good. There was a joke before that the brightest minds of IT work for Facebook, just planning how to get our attention to click through. So this is cool. They're pivot into the healthcare.
Yeah. Well, again, that's one of the reasons I do these talks. Like, there is so many jobs, and it's just, they cannot find people. And, you know, as I work with these apprentices, as I mentioned, one of the things that I try to do is just bring somebody along every time I get a contract, and turn that person into yet another full-time person, because I'm in the point where I don't really want a full-time job. So I just do contracts and then kind of get people into the industry one by one, because there is such a need. I mean, it's just like, I turn down work every week. And so, you know, if you want to do it, don't be intimidated by lack of knowledge. As long as you're willing to learn, you can make a contribution. And I mean, it's so meaningful. Like, if I can be part of a group that starts to get the rapid clinical out to hospitals, wow. I mean, you know, that's something I really want to do as a technologist. So, and it's also really fun because, like I said, these cloud vendors are just duking it out between each other. And so cloud is already evolving quickly, right? Serverless is evolving quickly. And now I'm kind of like at the tip, right? Because they're really pushing it in the genomic space. I mean, you really have to be kind of you know, if you like stability, don't do this. It's like the least stable, right? But you know, incredibly rewarding, incredibly challenging, and the people are great. You know, the people that are in the research area, they're in it because they care, right? You know, you do have to find a common language. Because again, it's kind of funny, I think, that they're intimidated by technologists. I'm like, kind of like, you're the doctor. I just know how to fix, secure a bucket. I think you win. But, you got to find that common ground. And then, like I said, be in service to what they're doing. This is the thing that I see technologists doing wrong. And it's not even really on purpose. It's just because we're engineers and we want to optimize, right? Like optimize this, use the most optimal thing. Well, the most optimal thing is not the fastest thing. It's the thing that they can use. And that's real hard to take, because there are more optimal things out there that we can use because we have more technology experience, but it has to be the most optimal thing that they can use.
And you're tying nicely to the beginning when the intro slide, I said how we are technologists who like people in the cars instead of having the business drive it. You're giving the purpose to what we do. Thank you.
Yeah. So, Yeah, if you want to get started, the thing I would say is go to the Team Terry and start reading about it. And then, you can just contact me and we can pair on a project. I mean, that's a great way to get started. There's also lots of open source libraries that I link to and reference. I created an open source course on GitHub called, and it's based on one of my Lynda courses. So I had this course on Lynda that's real popular called GCP Essentials. I call it the missing Google Cloud course because a lot of the materials in Google Cloud assume too much knowledge. So it's a really basic course. And when I was at the Broad, they use mostly GCP, although they're going to start using Azure now too. And I asked them, I said, do you have something for your researchers? And they said, no, we really don't. And so one of the things I did with them is I adopted that course, GCP Essentials, as GCP for Bioinformatics. And I put it on GitHub. So it's a completely free course. And it is kind of like notes, so markdown pages. And then I made short screencasts, like 3 to 5 minutes, like 50 of them, of each GCP service. And then I use bioinformatics data and bioinformatics examples. And, again, that's how I know so much about making these little hello worlds, because it was really difficult to find small data sets and to get like problems that ran in like a minute. Because again, sometimes I was shown like, oh, this is 8 hours. And I'm like, no, I'm not going to do a hello. No, that's not how people learn, right? And so that course has got some really good usage. And then because that was really well received, the Broad again engaged with me, and that domain-specific language, WDL, the workflow definition language for Cromwell, they asked me to make an open source course, and I made one on GitHub. Again, same concept, that because they want to really have that language in service for the greater bioinformatics community. The Broad is a nonprofit, albeit a well-funded one, but they are a nonprofit, and their idea is to make tools, libraries, and patterns for the greater research community, to make reusable stuff, basically. So I have a lot, I've left a trail there. On the Amazon side, that use case that I talked about where I went from 500 hours on-prem to 10 minutes, I wrote a series of Medium articles, and that's the data lake, the native data lake pattern, and I have links to all the repos and everything. So again, I've left a pretty comprehensive trail if you want to, jump in and get started, because there's so much to do. It's like just go.
This is cool. And also Google invited you to Cloud Next last year to talk intro about the toolkit you created. So that's a good overview for folks getting in.
Yeah, on the Azure side, what's really interesting is the Broad announced that they added Azure as a second cloud. So they have an entire platform. It's called Terra.bio, and it basically is a web UI that encapsulates Cromwell and WDL, and it presents in a more friendly way for the bioinformaticians these workflows that they can just configure and put their data, and that runs on GCP. And the Broad announced that they will be adding Azure as a second cloud because, again, they are not tied to any specific cloud. Their mission is to create these tools. So Terra is completely open source, and that's another area to look at. So again, there's just, you name it, and somebody else asked about benchmarking. That's another area I'm working on with a company to kind of try to develop these benchmarks, like a TPC kind of thing, because that would be so incredibly useful. So there's just so much work to do.
Wow, this is amazing. We still have I don't know if you're rushing, we still have 15 minutes. But any other questions? And this is all accidental as well. Like when I invited you originally, I was reading this book of data platforms, and you are the expert on all 3 clouds. And in one of your pre-COVID talks, you were talking how genomics is big data. So that was my inspiration. I had no clue what we're going to learn today. So thank you so much.
Oh, for sure. Well, again, one of the things, one of my resolutions for 2021 is to get away from the PowerPoint. So sometimes that makes things more concise, which maybe that's good. Maybe that's my talk optimization. I don't know. You tell me. But I have the article. I have the I have the video that you can actually watch if you want to try it out, if you want to like try a pattern. It's really like, what do you want to get out of this? Like, do you want to actually build something? Do you want to, know where to study next? That's really where I can be your guide, because I've got several different things you could just go and build if you wanted to. Or do you want to try to apply some of these patterns and learnings to your own domain? So.
When you say you mean everybody in the group.
Yeah. Yeah.
And that's the last one's probably the most common, where people, it's the theory that you can then apply to the area that you know best, and you've lived through the wars of having to, rework this massive workflow 100 times, and that's where I think the learning really comes from. What was the name of the quantum book you had held up earlier? Which one was it?
Yeah. So it is Programming.
Oh, it's O'Reilly. Okay.
Yeah, Quantum Computers. Yeah, it's an really interesting book. Yeah. Again, how this applies to problems like genomics is basically the state of quantum computing, which you can get in the cloud, by the way. Amazon bracket is quantum as a service. Google will have it shortly. IBM has it. And Azure has quantum service. They also have Q#, which is the Microsoft quantum language. So you have to learn how to decompose the problems, because you have a classical portion and you have a quantum portion. And the analogy is, I don't know if you guys have done any machine learning, but like with TensorFlow, where you have CPU and you have GPU or TPU, you offload some of the linear operations will run faster on a TPU or a GPU. TPU is a Google Tensor Processing Unit. It's a Google optimized chip, basically. So this idea is actually really important as the amount of data advances, that whether we're machine learning on it and we're using TPUs and GPUs, whether we're doing using some sort of computation that can benefit from FPGAs, or whether we're going to use QPUs, quantum processing units. This area is very interesting to me, figuring out how to decompose the problems and figure out what's the classical portion and what's the non-classical portion. I think it's actually going to be extremely significant as the data volumes go up.
I was wondering about that, actually. You talked about the TPUs, which I hadn't heard about. And, this is really underlines the value of standards. And of course, the thing with standards is everybody has one. But, when you talk about hardware optimized processing, and you talk about the scale of these problems, and you talk about the power of the cloud vendors, it seems like a perfect storm to me for them to build, and certainly in their interest, but ideally some sort of standard that is not locked to a particular vendor, hardware optimized workflows to solve these very big problems. And, granted, there might be a trade-off, but, these data sets are just going to get larger, and these are big problems that will serve humanity in the long term versus, somebody's bottom line, even though I'm sure somebody will find a way to turn that into beneficial to their bottom line. But so I was wondering, like, what more do you know or have heard about with regards to hardware optimized solutions and or pipelines for these specific types of data sets?
Well, I'm not seeing, I'm working with a ISV that's doing one for rapid clinical diagnostics, as I was saying. But I'm not seeing the cloud vendors do that for verticals yet. Now, I am seeing Amazon announced last year that for their data warehouse service Redshift, they have the Aqua Accelerator, which uses FPGA, and it's all automatic. So for certain workloads, if you could take advantage of the Aqua Accelerator, some of the computation will be offloaded. So they more, in the case of Amazon they more built it as a enhancement to a service rather than for a workflow. So more generic. Google, of course, is doing tons of stuff with examples for TensorFlow. So they do have some vertical specific workflows, machine learning workflows that use TPUs, because they have the more optimized GPU. It's a differentiator in the Google Cloud, because GPUs are, they of course differ like any hardware, but they're sort of more standard across the industry. So you can get GPUs in Azure and AWS and Google, but the Google super GPU, the TPU, is super expensive and super optimized. So differentiating on the hardware offering is interesting. And Amazon having FPGA now as an option with EC2 instances, because I don't believe Google has that at all yet. So it's kind of a trend for high performance problems that I'm seeing that I think will apply to genomics. So it's certainly new for me. I haven't worked in this long enough to have done much with specialty hardware. Maybe some of you have, but I haven't.
Yeah, I mean, that couples well with kind of the long ensconced mindsets. You talked about R. Why are they learning R? Because why are they using R? Because that's what they're learning in school. So, like, how do we get to the source of the problem? Saying, please stop using that. Here's a tool that's going to serve you in the longer term. So there's some kind of social issues there. And actually, I was even going to ask you, even though it's kind of way off in the left field here, like, do you think that there's a value of folks out there kind of evangelizing for a rethinking of how to solve their problems, and not telling them how to solve their problems, but understanding more so that they'll get greater efficiencies if they're really willing to step back farther and farther and farther, even to the fundamental tools that they have initially tried to utilize, and rethinking that the tools are out there. Granted, it's kind of ripping things up by the roots, but do you think that there is a willingness to even accept that perspective, considering the folks that you've met in this space?
Well, I think data is always like the driver of change. So, one of the things around this cost problem, because it is a problem, is, and it's one of the reasons I'm really interested in doing benchmarking work, is what if, for example, Kubernetes is n times faster than something like Cromwell, like n being a big number. Like, will that drive the Cromwell team towards faster integration of Kubernetes? Or, how can we merge best practices quicker? The BigQuery with SQL against VCF files is something that is, I'm just a big fan of BigQuery, and I'm just like, rather than writing all this blah, 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 if you can just write a SQL statement in a serverless fashion, gosh, wouldn't that be great? But again, that's so far away from what people are doing now that what I find in general, and this is my focus in education, if you have somebody who's here and somebody who's here, then what I try to do is build the bridge, right? Build the steps. So, like, very specifically with BigQuery for genomics, there was just this assumption, like, okay, here's the SQL statement, right? And so I tested it. My instinct was researchers aren't going to know how to do this. And, they were loath to say they didn't know how, but I finally got them to say it. So then I just decomposed it, because I actually found a class out there, but it had too much assumption of knowledge because it was written by a SQL DBA. And so, like, it went into subqueries after 3 queries, right? And like, no, you have to go select from where. You have to go, first we select from, then we select from where, then we select from where order by. Like, you have to build the bridge. So,
Do you have a course in that too?
Do they not need the full array of computation? Like, I'm just thinking, like, it's funny to knock R, but if you're doing complex matrix algebra, is a lot easier to do in R than it is SQL.
Right.
It's the right tool for the right job. So I don't think you could say that everything needs to be simplified to an SQL, but maybe they're not doing that type of computation for their tertiary analysis or whatever the analysis is. Maybe that's done earlier on. Is that right?
You'd be surprised how simple for example, the machine learning is. Like, I'm not an expert in machine learning, and I was like, oh my God, this is going to be horrible. Everything's going to be a neural network. Everything's going to be TensorFlow. It's a lot of logistic regression. Mm-hmm. It's a lot of logistic regression, which I can get that, right?
Mm-hmm. And XGBoost, it's like penicillin, 80% of problem solved.
Right?
Unbelievable.
Right?
Yeah.
So yeah, you are right about using the correct tool. But again, I cannot emphasize enough how much I see technologists over here, researchers over here. They're not talking to each other. Yeah. They're intimidated by each other. It's like you see in every business, but it's sort of worse because, I don't know, the stakes, it's it's worse than what I've seen in other industries. So if you can just sit down and instead of saying, oh, I think you should use Kubernetes, just like, what problems are you working on? What are your challenges? What do you wish that you could do, but doesn't even seem possible? And then move towards that. I'm very much like a lean startup kind of person. So what's the minimum viable process? Like I really think that way. I'm really decomposing the problem. I think that's really been a technique that's been very helpful. Because again, they're thinking like the whole pipeline, the whole data set, the whole 27 steps. Like I need the whole thing. And I just can't get from here to here. It's that same thing, right? Break it down. Like what are the first 3 steps of the pipeline? What is the first, 1/10 of the data? Let's get that running optimally, right? It's not honestly that difficult. It's kind of the same thing over and over. Because what you have is these people that have kind of been put in this fast race car. And you just kind of need to be like sitting next to them going, are you tired? Do you need a break? You know what I mean? Because and there's a lot that can be done like really small. I'll make an example. I'm a really big believer in visualizations because when you have massive amounts of data, it's a well-known thing that rather than a big list or a big whatever, if you have a picture or a drawing, the cognitive reception is faster, right? And so one of the things that I've talked about with a lot of these bioinformatics teams is visualizing the workflow, just like we visualize our architectures, right? And I mean, I almost cried when I saw that when the Broad put out their COVID reference workflows, for the first time in their examples, they put visualizations. And it literally, in the wiki, and literally other researchers said, this was so easy to use, and I was able to use it immediately. Because the tendency in scientific research is just, right, when you're explaining the tool, and that causes a lack of adoption because you can't understand it, you can't parse it. Whereas if you have the picture, do this, do this, do this, do this in a workflow. And, that was a little tiny influence. But I mean, if that caused researchers around the world to use those workflows on the cloud, it was worth it,
It's awesome. Would you come back to talk about something else?
Well, this is it's going to be more of the same. I hope we don't have as much to talk about with COVID. Yeah, but thank you. I mean, I know it's a little bit unconventional, but I promise no PowerPoint.
It's good.
So
felt like a class, really.
Yeah. Well, again, I hope that I've given you some useful information, and I'm easy to find for any sort of follow-up or collaboration. And all my resources are out there. It's my big hope that people will find value and use them. And they're on GitHub, so you can, if there's mistakes or suggestions, you can do pull requests.
Cool. Hang with us. I put your name for the book raffle from, like, you read books, but it's good to get a gift. So we use this tool, Wheel of Names. Not too many people put their names. So as you were talking at the end, I was cutting and pasting names. Whose name am I missing in the list here? Anybody?
One last question in, Daniel? Or
Go ahead. Yeah. We still have time. I just want to be, it's 8 o'clock. I don't want to keep people who don't want to stay.
Sure, Lynn, I was just going to say, do you think that big data is like a dirty word at this point, where it's really scaring people away and creating like a segregation in the technology community where people say, oh yeah, I don't do that. I don't work on that. Meanwhile, they're perfectly capable of applying their knowledge to solving some of the problems. So do you see it as something that really needs to be de-vilified?
Again, I'm kind of in this different world where I'm post big data, I call it genomic data. Like, big data to me is like so overloaded, it doesn't even really mean anything anymore. I mean, who doesn't have big data? I just laugh, like, oh, I have 1 terabyte of data in my data warehouse. I'm like, my client puts in 45 terabytes per day. So I don't know, maybe I'm being too glib here, but everybody has big data. It's not meaningful anymore. It's more like, how are you going to evolve? Are you going to start using a data lake? Are you going to start using a lake house? Are you going to what is your sort of solution for the data that you have to deal with? Because if you're just using a relational database in a data warehouse, that's not probably gonna do it anymore for most people. So I don't know if that's a direct answer, but that's what I'm seeing.
Yeah, I agree. I just think that scale doesn't matter anymore.
Yeah.
Any other questions? I'm not rushing anyone. We can stay.
Well, why don't you do the draw first, and then we can still stay.
Okay.
If people want to go.
Anybody else wants to win? From Manning, you can get either course or video or live project, anything you want. I see more people. Anybody? Sina, you want to?
Thing not in.
Okay. So the only thing is you'll have to contact me to put in the chat your email address so I can. Anybody else? I cannot even cut and paste this. CO. I'll put like this. CO. How do we pronounce your name? So okay. So let's do this, huh? Good luck. Who is it? Sina or I?
Hey!
That was funny. Okay, I'm stopping presenting. Sina, send me email into the chat so I can introduce you to Manning Fox. And I'm stopping presenting. Any other questions, guys? So I can. Thank you, Lynn, for coming here. I look forward to learning more from you. Now we know you have a book. You were telling us about the book club before you go. So who are the people you want us to reach out about?
Yeah, let me just give you, because I can't have my DMs open on Twitter because I get too many weirdos. So I'm going to, if you DM this guy, Jeremy Clark, Jeremy Bites, I'll just get hit just a second. And then just go, I want to join the book club. I'll put it in the chat just a second. Only I would come on and talk about genomics. Quantum on genomics because I'm such a nerd.
And if it wasn't for you, I would ignore the area like it.
Well, it's when Amazon announced Bracket, that's when you can when Amazon announces a service, that's when it's commercially viable because they don't do anything just for academic, right? They are their business people, right? Right?
You're right.
Like if Google announces it, you don't have to pay attention.
So
but
it's like a Starbucks. They open a shop, you open your business there.
Exactly. No, it's, I have just been loving learning about it. It's so hard though. Oh, it's just so brain bending because the math is a lot. I enjoy math, but I just, again, I've learned math so piece by piece, and that's not a great way to learn math. Math should be learned, one topic after another, kind of, you have to have the foundation. I've really struggled with that, but I enjoy it. It's kind of, just as an aside, one of the things I've actually thought about is to go to school and get a degree in math because I never had proper math education and I just love it. And I've only learned it kind of like as needed. And I feel like I would be, happier. So I've actually thought about getting a math degree.
Whatever we know, we think there is something else that's missing. I felt the same about statistics. When machine learning came, that was the area we never had that electrical engineering. Math was no problem, but statistics, we never had it 30 years ago, like when I finished.
Yeah. So, but then I feel like, I want to keep working with these bioinformatics clients because, like I said, every time I work with them, it's just the simplest things, but it really does make a difference, right? And then if I can it's a sort of a double hit, like really help them. And then if I can get more tech people into the industry, that seems like the best use of my energy. Do you know?
This is awesome. And an internship program that you have, that's something, I don't know if you still have time, like it's after 8, I could chat with you longer.
It's really informal. And again, I've just written everything on Medium because I get asked so much and I just direct people to the Medium thing. And what I do is, because I get like, will you mentor me? Will you mentor me? No, I will not, because mentoring is just talk. I want to actually work. And, plus I want it to benefit me, to be honest with you. And so I say, okay, well, we'll pair program for like 1 or 2 hours just to make sure it's cool. And after that, I'll hire you. And then I hire people and I pay them, not a full rate, but a decent rate. And then they show work experience working with me, which also helps them. And I just dive right in. Like I literally just like the first day, okay, we're going to set up this Azure. I mean, the woman that wrote this article with me, she was a public school teacher and she was my LinkedIn student and came to me and said, I really want to make a career change. And I said, okay, you ready to work? And this article was one of the first things that we did. I was like, Kelly, let's build this. And she knew no Azure, nothing, no bioinformatics. And I was like, let's go.
And that's an amazing way to scale a little consulting business as well, because people either to go to outsourcing or like how to find people to help you to grow. This is perfect. And it's your own style. Like when you had, you were talking about your father in one of the videos. That's the way I pick up skills.
Yeah, I mean, it's very much like the trades, like the construction, construction or plumbing or electrician, because my dad was a lineman, like for electricity. And so that's kind of where I learned that process of apprenticeship, where you work with a senior person and you work with them. And I actually really think that it's kind of the missing thing in the software industry, because you have all these academically trained students that don't know what a database is and they don't know what the cloud is, but they can do a bubble sort, right? So what? Okay, yes, that's good, and so, and I think that actually it results, frankly, in a lot of societal problems, because they're all in California and they get all this venture money and they build things that are, I call them replacements for their mother, right? They just, it's this culture of youth that is causing a lot of doing a disservice to our industry. So, in other places, in other industries, experience is respected. Another place that does this is Germany, very much does an apprenticeship model around, building things and mechanical things. And, I just think that it's something that our industry should really be thinking about. It also provides paths for people who were educated in non-traditional ways, like me, because the industry is very focused on, what school did you graduate from? Do you have a CS degree? Can you do algorithms? And there is a certain set of problems for which that is necessary, but there's a whole bunch of technical work that is only minimally necessary, if at all. And by focusing our hiring practices on that subset, we are perpetuating this exclusionary nature, which is, I've been working in this now 15 years, and for example, the amount of women in tech has not changed at all. It's lower. So all the things that we've been doing have not been working. And I know apprenticeship works. Like, I don't specifically pick women, but they tend to gravitate towards me. And, I had like 20 people and 15 were women. They're all employed. They're all employed either better jobs, or they were coming into tech. These are 15 women that would not have had these jobs. So the question is really how to scale this. I've been actually talking with the big vendors, Microsoft in particular, because here in Minneapolis, as you might know without going on too long, we have a very big racial wealth inequity problem. And I didn't know this until I moved here, but we do. And, we need to really address this racial wealth inequity problem. And one of the ways I think we could do that is by having tech apprenticeships for people of color. Because, again, oftentimes they don't have the same educational opportunities. And so they're not in that subset that is considered what is wanted. But given the data set I've had with women, I feel like I have, at least this small data set, 15, 20 people. And so I'm actually pitching this to Microsoft for the Twin Cities.
Well, maybe we can help as well. That's a good topic for one of the meetups, because we need help, as lots of us are consultants, and we don't know how to kind of work on that.
Yep. I know. So anyway, well,
Thank you.
Me, I'm good at talking. So
hopefully enjoying it. So.
Hopefully this wasn't too off the wall. I don't know, but
Not
I did.
Excellent.
Fantastic.
I'm glad that, some people, you guys were talking and interacting. So, I really want it to be very conversational. One other thing for you to think about, because this was in my mind as this is an experiment. I don't know if you guys are on Clubhouse, but I'm trying to see how I can make my talks more interactive that are virtual, because I'm just tired of PowerPoint.
So Clubhouse is on iPhone only. Like I tried, I got a couple invites. I couldn't do anything with Android.
It's on Android now.
So it is, okay. I just gave up. I was like, gee, that's for kids, for my daughter.
Now it is kind of like West Coast, like, blockchain and all that kind of stuff. But I'm just interested in the medium of the semi-moderated, very similar to what we had here, where you have people that know each other in rooms. And then interestingly, sometimes people are Twitch streaming to have a screen. It's so interesting because I'm like, from a meta point, I'm thinking about, I really just don't want to do PowerPoint lectures anymore. I just really don't want to do them because I mean, I could record them and people could watch them, but in terms of a user group, like I don't want to do that anymore. And maybe that's just my own problem, but I don't want to watch them and I don't want to deliver them. I want to have conversations with people.
Yeah, I really appreciate you calling out the mentorship piece, Lynn. I mean, that's fantastic. And, you're not just talking the talk, you're walking the walk, which so you're a real role model with regards to that. But I mean, we as an industry are definitely lacking there. And that actually jives completely with what you're saying about, PowerPoint presentations and such, because it's really about conversations and relationships and ways that people can actually outflank these ridiculous HR systems and education systems that are not serving anybody save for the people that propagate them. So kudos to you and really appreciate everything you're doing.
For sure. Well, again, that would be something maybe to talk about. I wrote an article on Medium, of course, called Tech Anti-Interviewing, after I had a conversation with a founder in Berlin who couldn't hire anyone but white guys and he didn't know what to do. And so, again, I'm creative, if nothing else.
So cool. Any other questions, or you're going to go back to your families?
I'm getting hungry for dinner.
All right. Well, thanks for putting up with me. Thanks for inviting me.
No. Thank you, Lynn, so much.
Thank you so much.
Thank you.
All right. Take care. Bye.
Stay safe.